Alright, let's answer question 2 about rotations. Given this code fragment, what is the probability that a measurement would result in the state 0? So we have a quantum circuit here with a single qubit, and we're going to rotate that qubit about the y-axis 3 pi force. So let's gain some intuition into this before we answer it exactly. Qiskit initializes all qubits into the 0 state upon execution of the circuit. So our qubit will start here, and since we're rotating about the y-axis, we will rotate it along this curve. So we should expect to see no imaginary units, since that curve doesn't go in the y direction at all, and there will be no relative phase in the final result. If we were to rotate it pi halves, then we would get the 50-50% chance that the Hadamard gives us for measuring a 0 or 1. But because the angle is 3 pi fourths, which is greater than pi halves, we should expect to see the answer somewhere down here, final result, and a greater probability of measuring a 1, since it's closer to a 1, than a 0. So there should be less than a 50% chance of measuring a 0 than a 1, which gives away the correct result. We can eliminate all of these, and boom, there it is. Final answer. But to be assured that that's the right answer, we can calculate exactly what the measurement will be, the probability. All we need is two angles, and we can find the final state of the qubit using this formula. But since there's no relative phase, then our phi parameter is going to be 0, and the relative phase goes away. And so then we just worry about amplitude for the 0 state, cosine of 3 pi halves times, it's cosine of 3 pi fourths times over 2, which is going to be 3 pi eighths. And then sine of 3 pi eighths is going to be the amplitude for the 1 state. The probability of measuring of 0 is equal to the square of the amplitude for the 0 state in the description of the qubit, which is cosine of 3 pi eighths. So that squared is equal to roughly 0.146, which is equal to the answer C. And we can generalize this. The probability of measuring any result in the description of the qubit is equal to the sum of the squares of its corresponding amplitudes.